Hello and welcome to this video on the design and analysis of machine learning experiments presented by EDU Onyx. This video is going to be a part of our Unit 5 covering real-world machine learning, and we're going to talk about analyzing the performance of algorithms and comparing and contrasting the results that they provide. A lot of the time what you're going to do is you're going to have your problem, you're going to have picked an algorithm or hopefully several, and now you want to figure out which one's the best. And this video is going to hopefully answer how to do that. So we picked an algorithm that we think can solve our problem. Now how do we make sure that it actually can? What we need to do is we need to start by stating the problem clearly and defining what the objectives are. So this is going to be the aim of the study. We may be interested in assessing the expected error or some other response measure of a learning algorithm on a particular problem and check that, for example, the error is lower than a certain acceptable level or threshold. Or perhaps what we're trying to do with our study is given two learning algorithms, or even more than two, and a particular problem as defined by our data set, we may want to determine which one has less generalization error. So which algorithm out of our several of options actually performs the best. The next step is going to be the selection of the response variable. So we need to decide on what we should use as the quality measure. Most frequently, error is used, and that is the misclassification error for classification and the mean squared error for regression. So having a response variable is ultimately important as well. If we're doing something like unsupervised learning, what acceptable level of clustering or dimensionality reduction is going to be acceptable? So that goes into the selection of a response variable as well. The next thing is choice of factors and levels. So what the factors are depend on the aim of the study that we defined in step 1. So if we fix an algorithm and we want to find the best hyperparameters, then those are the factors. If we are comparing algorithms, the learning algorithm is also a factor. If we have different data sets, the specific data set becomes a factor as well. So the levels of a factor should be carefully chosen so as not to miss a good configuration and avoid doing unnecessary experimentation. So for example, testing every single algorithm out there would be a good way to find the best one, but that might be some seriously unnecessary experimentation. As a result, we're only going to pick a couple to test. So finding that combination of or level of factors that we're not missing good solutions, but we're not doing unnecessary work is going to be important. The next step is going to be the choice of experimental design. So it is always better to do a factorial design, which we'll talk about a little bit more later, unless we are sure that the factors do not interact. So replication number depends on the data set size, and it can be kept small when the data set is large. So we don't necessarily need to repeat depending on our data set, and we're going to talk about experimental design in more detail later. So the next step would be actually performing the experiment, carrying it out. There's some things that we can do when actually performing this step so that all the results become reproducible. Reproducibility is going to be very important, and we want to avoid bias, and by bias maybe some of our preconceived bias or maybe biases towards certain learning methods. So that's going to be part of performing the experiment. The next step is going to be statistical analysis of the data. So we want to analyze the data in a way so that whatever conclusion we get is not subjective or due to chance. So we're going to have some different methods for statistical analysis to make sure that doesn't happen. And finally, we get our conclusions and recommendations. And so once all the data is collected and analyzed, we can draw objective conclusions, because ultimately that's what we want to do when performing a machine learning experiment. So let's look at some of this in a little bit more detail. The first, factors, response, and strategy of experimentation. So when you are performing an experiment, you are going to have controllable factors and uncontrollable factors. The parameters are going to be factors that you can control. The type of learning algorithm is a factor that you can control. There are some uncontrollable factors like the random initialization of the weights. Maybe you get a better option one of the times when you initialize it. But ultimately, all of those factors are going to combine to give you a specific output from your input. And so when you're actually performing your strategy or your actual experimentation, there's a couple different ways you can do. If you have two factors, so maybe the type of learning algorithm is one factor and then the specific data set is another, you could do a best guess and simply move in a couple directions and see which one ends up working better. You could do one factor at a time, which would assume that your factors are independent. So we'd go from all the way small to large on one factor, and then small to large on the other factor, and see which level is fitting for each. The last solution is a factorial design. So when available, you should always do a factorial design simply because it is guaranteed to not miss any optimal configurations. A lot of the time we don't have the resources or time to do a factorial search, but if you can, this is the best strategy of experimentation out there. So you want to do that if you have the resources and time available. Next thing that we should talk about is randomization, replication, and blocking. So the three basic principles of experimental design are randomization, and this is going to ensure that all the results are independent. In computer science, even things like the computer warming up can change the outcome of or our results. So we want to randomize the order that we're running our trials in, and randomization in general is a great way to account for variables or uncontrolled factors and variables that we aren't aware are there. Another thing is replication, which is going to average the effects of uncontrollable factors. So what we want to do is reproduce this several times so that we can show it was not simply due to chance that we got the output that we did. The last thing is going to be blocking, and this is going to reduce the variability due to nuisance factors. So blocking becomes important when you are performing these experiments as well. And blocking is actually where we're separating our data into like our training set and then our validation set and test set as well. Breaking up the data in that way ensures that we're able to generalize and we're not overfitting or other things such as that. Finally, we have cross-validation and statistical analysis. So cross-validation, which is the repeated use of the same data split differently, is again going into that blocking where we're separating out a validation test set and as well as a training set. And remember, as soon as you do the validation step, the algorithm has essentially learned from that validation data, and so that now becomes part of the training data. But cross-validation is always important because it shows that our algorithms can generalize. And you can do that using a k-fold cross-validation. A k-fold would simply be splitting the data into a k number of equally sized chunks of data. So maybe if we have 10, we split our data into 10 equal sized chunks, and then you'd run the experiment 10 times. Each time, 9 of those chunks would go into your training data, and 1 chunk would be kept aside for the validation. So this ensures that you don't get any weird data in your validation or any one type of data. Maybe all your positive examples are in your validation test set and none of them are in your training data. That would be surprising, but again, you want to do some cross-validation steps to ensure that something like that doesn't happen. And then you're also going to do a statistical analysis, and this is going to be what is used for actually comparing the algorithms. We're not going to dive into the statistics too much here in this video simply because of time constraints, and this is again an introductory course, but you're going to want to do hypothesis testing much in the way you would for any scientific research problem. So you're going to have a null hypothesis that the two algorithms are not significantly different, and then you're going to test that they are based off the number of inputs that you have and the difference in results. So you want to show that your results are statistically significant and not just due to random chance. So that's an important last step, and once you do that, you can really say with confidence that your conclusion is objective and true. So this is just a brief overview of the design and analysis of machine learning experiments. Whenever you're developing these algorithms, you should make sure that you do your due diligence and you explore all the possible configurations with the time that you have available. and that you test your algorithms and you do statistical analysis to prove, yes, these results are statistically significant and this algorithm is objectively better at this particular task. So thanks for listening to this video. In the next video, we're going to talk about some of the common software that is used in industry to actually design and develop these machine learning algorithms. So keep listening. Thank you very much.